All right, so as a reminder, 3-1, we're going to continue, but we're going to cover exponential functions and their graphs. So first of all, what is an exponential function? We're going from rational functions to exponential functions. Rational functions are polynomials in the numerator or denominator. So the x would be in the base of your exponential function. It might say something like x squared. I'm sorry, in your rational function. An exponential function takes the variable and puts it in the exponent. So that's the difference when you're looking at them. If I was looking at f of x equals 1 over x plus 3, that's a rational function. If I'm looking at an exponential function, it would be f of x equals, even if it was 1/3 to the x, something like that, but the exponent moves, or the variable moves to the exponent. So that's how we know the difference, okay? But there are asymptotes, like there's a little bit of overlap. So the parts of our exponential function are the base and the exponent. The thing being raised to the power is called the base. And then obviously what it's being raised to is called the exponent. That base can be a whole number. It could be a fraction. Okay, it could be a decimal. But that base should be bigger than 0. So a should be bigger than 0 and not 1. Because 1 raised to any power stays 1. That's going to be a constant line. So these things will have either exponential growth or exponential decay, meaning they will be increasing or they will be decreasing. So the very first thing we're going to do with these is literally just use our calculators to learn how to work the exponents. So it says evaluate the function at the indicated value of x. Round your answers to 3 decimal places. And A says f of x equals 0.5 to the x power, where x is 1.2. So when we're typing this in the calculator, we'll literally do that 0.5 and then your little caret symbol and then 1.2. And you're going to round to 3 decimal places. So 0.5 to the 1.2 gives you 0.4357. So it would just round to 435. And then B is 150 times 2 to the x power, where x is a negative 2.5. Your exponent can totally be negative. What does a negative exponent normally do? It moves it to the bottom. So it's going to take that 2.5 and really make it, it's going to take the 2 and really make it a half. But your calculator does that for you. You don't have to do that. So I would get 2, then I would raise the caret to the negative 2.5. You either have to group it like that, or you could do 2 to the negative 2.5. Make sure you do the negative. That's the leading one. That's underneath the 3. And then multiply that times 150. Or you could let your calculator do it all in order, but you got to make sure that you group it. This would be 26.517. Questions so far? So the way you'll see calculator use on these will be something like that, or it could give you like a word problem when it starts talking about bacteria growth or exponential decay or something like that. And you literally just have to know like what to plug in and then type it in the calculator. The calculator does most of that work for you. We're going to come back to slide 10 introduces the one-to-one property. This is also an algebra 2 skill, so hopefully you remember this, okay? But it says that for a being greater than 0, so my base has to be positive and not equal to 1, then a to the x would equal a to the y if and only if x equal y. And all that means is if the bases are the same, then I can set the exponents equal to each other. So if I had something like 2 to the x equals 2 to the 4th, that as long as the bases are the same, I can totally disregard the bases, just grab the exponents, and I would get x equals 4, okay? We're going to do a little bit of work before we get to that point, but that's the idea of the one-to-one property. If I can get the bases to be the same, then I can set the exponents equal to each other. The other thing you want to remember is that anything raised to the power of 0 is 1. So I could have something like 2x to the 3rd, y to the 4th, z to the 5th, and raise it all to the power of 0. And that answer is 1. Doesn't matter what's being raised to the 0 power, the answer is 1. And it's not like you can do a factor tree on these to figure it out. Like there's no other way to know that. Your calculator will tell you that. But if you didn't have your calculator, that's one of those things that's just literally like memorization that you have to know that anything raised to that 0 power is 1. So when we see the one-to-one property, you'll see it applied in this way. It literally says solve using the one-to-one property. So our goal is to first make these have the same bases. The rule is to take the larger base and break it down as the power of the smaller base. So instead of going up from 3, I want to take 9 and rewrite it as a power of 3. 9 is the same thing as what? 3 squared. So I'd get 3 to the x minus 2 equals 3 squared. And then as soon as those bases are the same, I set the exponents equal to each other. So x minus 2 equals 2, and then solve for x, add the 2, and I get x equals 4. These are easy to work backwards and check too. Like if I take that 4 and I plug it back in, I get 3 to the 4 minus 2, or 3 to the second, which is 9. Now go to B. I want these to be the same base, okay? There's a lot of different ways to do this, but you can change both sides. So if I wanted to make the 1/2 become a 2, what did we just say moves a number from the top to the bottom, or the bottom to the top? A negative on the exponent. So 1/2 is the same thing as saying 2 to the negative 1. And then 16 is 2 times 8, or 2 times 4, and 2 times 2. So 1, 2, 3, 4 2s. So 2 to the 4th power. You will never get these without a calculator and not have something that's a factor of the other. Like they have to break down to have the same base. There's a way to do it with a calculator, but we'll get to that later. So now I would multiply these exponents, because when I raise a power to a power, I multiply, and I get 2 to the negative x equals 2 to the 4th. And the bases are the same, so negative x equals 4, and x equals negative 4. Questions on that one? All right, and then what am I going to do with C? 6 to what power gives you 1? 0. There's no way to break down 6 so that it has a base of 1. That's, again, one of those that you just have to memorize. Questions on any of that? We're going to stop here. Like I said, I just wanted to give us a head start. Okay. What we're going to spend a good chunk of today's time on is graphing exponential functions. So an exponential function, if you just look at the picture on the bottom, can go two different ways. If the exponential function has a base that is a whole number or something bigger than 1, then my exponential function will increase as I move from left to right. So if this said something like 2 to the x or 3 to the x, something like that, then it would increase as you move to the right. It has a horizontal asymptote at 0, because if my base is positive, no matter what I raise that to, it will never be 0 and it will never be negative. So it will never cross the x-axis unless there's a horizontal shift, okay? If the base was a fraction, like a half raised to the x, then it decreases as you move to the right, but it still stays above the x-axis. There's still a horizontal asymptote at 0. All of this stuff kind of says, like, what are the characteristics? One of the important things is the domain is all real numbers. I can plug any kind of value in there. There will be a question on your test that asks you for the domain of an exponential function, and that is its answer. All real numbers, negative infinity to positive infinity. The range is 0 to positive infinity if it doesn't have a vertical shift. That will change if it has a vertical shift, which we'll talk about in a little bit. There is a y-intercept at 0, 1 on my parent function, because if I plug 0 into the exponent, then my base becomes 1. And then 3 says if b is greater than 1, it goes up. So if b is like, that would be the blue line that we drew. If our base is bigger than 1, it increases. If it is in between 0 and 1, then it decreases. It is 1 to 1 because it is a function initially, but it also has an inverse, which means it would pass both your vertical and horizontal lines. And then 6 says it has a horizontal asymptote at 0. It will get as close to that horizontal asymptote without touching it as possible. So when you are graphing these, you have to be careful to have that not cross your horizontal asymptote. Your horizontal asymptote will be part of what you graph. All right, so let's just talk about graphing from scratch. If I knew nothing about these values, then I would start with a t-chart. So if I had a t-chart, I would plug in -1, 0, and 1. And I plug them each into that 3 to the x. So I'd get 3 to the -1, which is what? 1/3. The -1 puts that 3 in the denominator. I'd get 3 to the 0, which is what? 1. And I'd get 3 to the first, which is 3. And then if I plot those points, I get -1 and 1/3, 0, 1, and 1, 3. Now what you have to be careful of is making sure you include your horizontal asymptote in your graph, because that, like, I can't go beyond the y equals 0 line. You have to be really careful, make sure it curves. So that takes you knowing that you have a horizontal asymptote at y equals 0. And again, that will shift if you have a vertical shift. If not, then we curve it so that it gets really close to that horizontal asymptote, but does not touch it. And then as we move to the right in this case, or it would be increasing at a fast rate. So what would be the domain of that graph? All real numbers, negative infinity to positive infinity. What would be the range of this graph? 0 to infinity. Does the 0 get a bracket or the parentheses? Parentheses, we can't include 0. It's not a point on our graph. What's the y-intercept? 0, 1. So there's two ways to get it, obviously, from our graph itself, but also it's the middle coordinate on our t-chart if we plot those three numbers every time. All right, go to B. So same thing. I'm going to plot those same 3 points, negative 1, 0, and 1. My exponent is a negative x, so I'd get 3 to the negative 1, or 3 to the first, which is 3. Good. 3 to the negative 0, which is just 3 to the 0, or 1. And 3 to the negative 1, which is 1/3. Good. And then I go to my graph, negative 1, 3, 0, 1, and 1 and 1/3. And again, we have to know horizontal asymptote is at 0. And it gets close to that asymptote without touching it. This time, my function is decreasing as I move from left to right.
Is it always that the horizontal asymptote?
Until you start to shift it up or down, which we're about to do. Yep. What's the domain here? All real numbers. What's the range? 0 to infinity with the parentheses on the 0. What's the y-intercept? 0, 1 again. Questions? All right, now let's talk about the comparison of these two. So if I have 1/4 and I have 4, and I do the same things, I'm going to kind of do the plug-in part of it quickly. If I take 1/4 to the negative 1, what do I get?
4.
Good. 0, 1. 1, so this is the 1/4 one. 1/4 to the x. 1/4 to the negative 1 is 4. 1/4 to the 0 is 1. 1/4 to the first is 1/4. Now let's plot the other one. So same three numbers, negative 1, 0, and 1. And this time it's 4 to the x. 4 to the negative 1 is 1/4. 4 to the 0, 1, and 4 to the first, 4. So if I plug in those, negative 1, 4, 0, 1, 1, 1/4, this is my first one. And I plug in the second one's points, negative 1, 1/4, 0, 1, and 1/4. So in both cases, right, I had 0, 1 as my y-intercept. In both cases, I have a horizontal asymptote at 0 because we still haven't shifted anything up or down. And if you think about it, like 1/4 to the x could have also been written as 4 to the negative 1 raised to the x, or 4 to the negative x. So the shifts that we make in our bases can also change the shifts in our exponent. Like if I do 1/4, I could simply rewrite that as 4 to the negative x, and then that changes the reflection on my graph, which we're going to talk about in a minute as our translations. So 4 to the negative x would be a translation over the y-axis, God bless you, which is exactly what just happened. All right, so all of the transformations that we did with our parabolas and square roots and absolute values, all those things also apply to exponential functions. If we add or subtract something after the function, it causes a shift up or down. If we add or subtract something in the exponent, it would be as though it's inside the parentheses, and that causes a shift left or right, positive left, negative right. If there's a minus on the front of my function, it reflects it over the x-axis. And if there's a negative in the exponent, it reflects it over the y-axis. If there's a scalar multiple on the front and it's bigger than 1, it stretches it. It's a vertical stretch. And if it's in between 0 and 1, it's a vertical shrink or vertical compression. And if it's in the exponent, it's a horizontal shrink if it's greater than 1 and a horizontal stretch if it's in between 0 or 1. Most of these you can just do like by plotting points. The thing you have to pay attention to when we're talking about our vertical asymptote, a horizontal asymptote, is the vertical translation. This is going to move your horizontal asymptote. So if it's plus 2, it moves it up to y equals 2. If it's minus 2, it moves it down to y equals minus 2. Everything else you could pretty much figure out by plotting your points, but you have to understand that that vertical translation is going to shift your horizontal, which is going to affect your range as well. All right, so now it said use the graph of 4 to the x to obtain the graph of 4 to the x plus 3. What's that plus 3 going to cause? Up 3. So if my original one, I'm going to make this the pink. My original one had a horizontal asymptote at 0. It was negative 1, 1/4, 0, 1, and 1/4. This is what 4 to the x looks like. Now we're going to graph 4 to the x plus 3. Two options. Take your original points, shift them up 1, 2, 3, 1, 2, 3, and this would go off the page, but 1, 2, 3. And shift your horizontal asymptote. Or I could have simply plot points. So I would say there's going to be questions in which you get both and you can just shift it. But then there's going to be a question like on your test, I'm not going to ask you to graph both. It's just going to have you graph the second thing. So as long as you know your horizontal asymptote went up 3, then you simply could just plug in your points and plot it. But there are going to be questions that also say, compare this to this and what is the translation? And in this case, we would say it moved up 3. What's the domain of 4 to the x plus 3? All real numbers, negative infinity to positive infinity. What's the range of 4 to the x plus 3? 3 to infinity, gets a parentheses because it doesn't include it. What's the y-intercept? We shifted it up, right? We shifted up from 1. We shifted up 3 places. So, good, 0, 4. And our horizontal asymptote was at y equals 3. It's where the vertical shift is. All right. So if my original, like plot your original points again, we're at negative 1, 1/4, 0, 1, and 1/4. What happens if it's in the exponent x minus 2? It's to the right 2. So our horizontal asymptote is going to stay the same. We're just going to take and shift all of our points 2 places to the right. Does it change your domain? No. Does it change your range? No. Did it change your y-intercept? Yes, and we don't even have it plotted yet, but our y-intercept would be where x is 0, so it would be 4 to the 0 minus 2, 4 to the negative 2, or 1/16. Questions? So the graphing question, there's more than one, but the one big graphing question on your test is going to ask you to fill out a T-chart to answer horizontal asymptote, domain, range, y-intercept, and then graph it. All right, now we're going to use the calculators because we have something that's called the natural base. So that E is a variable representation for what's called the natural base. It is approximated as 2.7 or 2.7 if I make it even shorter. It's an irrational number, so it doesn't end and it doesn't repeat. It's kind of like pi, okay? So when we see E, it means just like 2.7. On the calculator, you're going to see a little button that says E. It's on the left-hand side above the ln. So next to the 4, above the ln, is a button that says E to the x, okay? And that is your calculator basically taking 2.71828 and raising it to whatever power you want to make it. So if I even just did second ln and you get e to the first, you will see E, that value. 2.718281828. This is how it's derived, so I don't ever expect you to have to come up with this on your own. But this is not just a number that they threw out there, just like pi was not a number they just threw out there. Pi is somebody took a circumference, divided it by the diameter, and got that every single circle would produce the same value. That's where pi comes from. So this is what would happen. If I kept raising, if I kept taking like 1 plus 1 over n, no matter what n is, and I raise it to the n, the bigger the n gets, this number starts to get closer and closer and closer and closer and closer to the same number. Eventually, it would always round to 2.71828. Like if I just kept going here, no matter how big I made that exponent, it creates that pattern, which is like that natural base, okay? Again, you don't need to know how to get it. Just know it's an actual thing. Somebody didn't just make it up, okay? So in a calculator, you'll see questions like this. Use a calculator to evaluate the function f of x equals e to the x at each value of x, and then round to 3 decimal places. So A says e to the x where x is 4.2. So you literally just do e to the x and raise it to the 4.2. So second, e 4.2, and I get 66.6863. So we're going to keep it as 686. And then B, 125 e to the 0.05 times x. You can type that whole thing in at the same time. 125 e to the 0.05 times 30. And I get 560,211. So you'll see E sometimes when it's talking about something that has exponential growth or exponential decay, something like bacteria growth, that kind of thing, usually involves something like that. Yeah.
Should we always round 3 decimal points?
The test will tell you.
Okay.
If it doesn't say it, well, the only time I wouldn't say it if it was money, which when we'll get to interest problems. Other than that, it's specific. Nearest 10th, nearest 100th, whatever it is, it will tell you. So just make sure you read it. Okay, now what if we had to graph this function? Okay, so obviously I can like just type that in my calculator and see what the graph is. But this says use a graphing utility to construct a table of values for the function. So we're literally going to make a t-chart. We're going to plug in the same 3 values that we plugged in before. And there's 2 ways to do this. One is do 4 to the e, or 4 times e, negative 1 plus 2. Type that whole thing in the calculator. Or simplify it, 4e to the first. And then you could do 4e to the 0 plus 2. And you could do 4e to the 1 plus 2. This is one option. What's the other option? What if you wanted to see the graph of it? What would you do? Good. Go to the y equals and enter 4e to the x plus 2. And you can hit graph and it will give you the general shape of it. Now, if you think about it, e is like a base of 3. So this is like taking something that has 3 as its base, shifting it 2 units to the left. So it should shift it left. And then 4 makes it tall, right? It makes it stretch vertically. So when I look at this graph, if you look at the graph on your graphing utility, that's what's happening. If I wanted to get those values without typing that in one at a time, then I can go to second, trace, and I can go to value, which is the first thing in your calculate menu. Type in negative 1, and I get 10 point, we're going to round this to 1 decimal place because you're not going to get more accurate than that on your graph. And then I can go second, trace, value again, 0, and I get 29.6. And then second, trace, go to value again, and go to 1, and I get 80.3. You can also use the table. The only thing I would say about the table is if your x values were decimals, you're not going to see them on your table. Good luck. Right.
So there's a lot of ways to get it.
Yeah. So -1, now these go from 10 to 30 to 80. So I'm going to change this scale. Okay. I'm going to actually go by 20s. 20, 40, 60, 80. I don't have to change the x. I'm going to leave the x. But -1 and 10.9 would be somewhere like here. Oh, not there. Sorry. Here. 0 and 29.6 would be about here. And 180 would be about here. Now, where's my horizontal asymptote? 0. There's no vertical shift, right? So my horizontal asymptote is still at 0. Questions? And if you look at the graph on your graphing utility, it reflects what we just did. Because the last topic in this section is your interest word problems. So these are based on interest being compounded a specific number of times a year or compounded continuously. There's two formulas you got to know. If it's compounded a certain number of times a year, like annually, semi-annually, quarterly, monthly, weekly, daily, anything like that, then you use this formula that says A equals P times 1 plus R over N raised to the NT. Your R is the rate in decimal form. So the first thing you're going to do is take the decimal that they give you that's going to be, or that the rate they give you in percent. You're going to convert it to decimal. N is the number of times of year. So if it was annually, it's once. If it's semi-annually, it's twice. If it's quarterly, it's 4 times. If it's monthly, it's 12 times. If it's weekly, it's what? 50.
4?
52 times a year, people. You have to know there's 52 weeks in a year. 52 weeks in a year. You don't do like, people like to do like 4 weeks in a month and then multiply that times. So that's wrong. There are 52 weeks in a year. That could be on your test, and I expect you to know it. You can't like raise your hand and be like, how many weeks are in a year? I'm not going to tell you, okay? And then the N is the number of times a year. So, T is the number of years. We already did it. If it's compounded continuously, this is things like credit card interest or savings interest, especially credit card because they like to charge you a lot of money. It will compound it so quickly that you can't compute it with a regular number of times a year. You use E as the natural base. So compounded continuously means like, let's say it starts now, then in 5 seconds from now, you're getting money compounded on your new balance. So all of these are not simple interest. Simple interest is like you earn 10% over the course of the year. So at the end of the year, you earn 10%. That's it. Okay. These are all compounding, which means like if I put $100 into an account and I earn money monthly, then at the end of that month, let's say I earn 2%. Then at the end of that month, I have $102 in that account. And the next month, I'm going to earn 10% or 2% of 102. So it's not based on your original one. That's what these formulas are doing, okay? When you see a question like this, it says, find the accumulated value of an investment of $15,000 for 2 years at an interest rate of 3.2% if the money is compounded, and those are 4 different questions. Semi-annually, quarterly, monthly, continuously. But they all share the information at the top. So for A, B, and C, I'm going to use P times 1 plus R over N to the NT. And for D, we're going to use PERT, P times E to the RT. P represents what? Principal balance. Principal, which means what's the money at the beginning. So in this example, what's my P? 15,000. R is the rate. What's the rate? 3.2%, and R has to be converted into decimal, which would be, move that decimal twice, 0.032. You don't need the leading zero, but you need the 0.032. The first thing you should do is move it. And t is the number of years, which in this case is 2. Now what changes for A, B, and C is your n. So if it's semi-annually, how many times a year is that? 2 times. So my n here is 2. If it's quarterly, how many times a year is that? 4. If it's monthly, how many times a year is it? 12. And then compounded continuously, we're going to use per. So for each of these, I would get 15,000 times 1 plus 0.032 over number of times a year, which is 2, raised to the number of times a year times the number of years. That's for A. If you have your graphing utility with you, you need to practice typing this out. If you don't, you need to make sure you are practicing this at home. Trying to do this on your scientific calculator, like your phone, is a nightmare because you have to figure out the exponent. You have to start with 0.032, divide it by 2, add it to 1, raise it to the power, and then multiply it times the 15,000. So practice it on your graphing calculator. You could type that whole thing in. 15,000, open your parentheses, 1 plus, get that fraction, which is the second y equals 0.032 over 2, close your parentheses, get the caret, 2 times 2. So it looks like this. Alpha y equals. So I get $15,983.29. But the money is one of those things I won't tell you what to round to. You have to know it's money, right? You don't make 0.286 cents. It stops at the hundredth. Yep. Round. Good question. If it didn't, like if it was open ended, I would take either. But for like WebAssign, it's going to ask you to round it. Yeah. Truncate means it just drops off. Literally, you ignore it. Yeah. Whatever digit you're at. So like you would go to the 2.8 and stop. But for money, we round. Yeah. All right. Now we go to 4. So here's a good tip on your calculator. If you arrow up to the equation above it and you hit enter, it will duplicate your equation. And then I can just change my 2 in the denominator to 4 and one of the 2's in the exponent to 4. So for quarterly, we got $15,987.31. And for monthly, we got $15,990.02. Questions on those? Okay. The more times a year you compound, the more money it's going to be. So like if you compare this from 2 to 4 to 12, 12 should be the biggest. And because E is compounding the most often, PERT should be the most amount of all of them. So for PERT, I'm going to do 15,000. E, raise it to the 0.032 times 2. And I get $15,991.39. I think on WebAssign it says like n equals 2 or n equals 4. Your test will use the words. So make sure you understand the difference between semi-annually, quarterly, monthly, weekly, whatever, daily. How many days are in a year? And don't be a smart ass and say like, what about leap year? In a regular year, there are 365 days. Okay. Questions on this? So the first thing you have to do, remember the very first thing you factor the top and the bottom. And then before you do anything else, you do domain. So I said the denominator is not equal to 0. And you get that the domain can equal -6 or +6. So negative infinity to -6, -6 to 6, and 6 to positive infinity. You have to do that before you cancel out your denominator with the top, even if there's a hole. Then you check for holes. This time there is. It crosses through the x minus 6 in the top and the bottom. That's the x coordinate of your hole. Then everything else you get from your new updated function. For my numerator, I set what's left equal to 0 to get the 0, which is -1. My vertical asymptote is going to be at x equals -6. The horizontal asymptote is y equals 1 because the exponents are the same. There's no slant. To get your y-intercept, you plug 0 in for x. And again, the updated one, so I'd get 0 plus 1 over 0 plus 6, and you get 1/6. So your y-intercept in coordinate point form is 0, 1/6. To get the y-coordinate of your hole, you're going to plug back in the 6 into the new one. 6 plus 1 over 6 plus 6 is 7/12. That's the y-coordinate. Then you're going to graph what you've got. So you've got vertical asymptote at -6, sorry. You've got a horizontal asymptote at 1. You have a 0 at -1 and a y-intercept at 1/6. So based on that, I know it has to be in that bottom corner. And the fact that there's no zeros to the left of the vertical asymptote tells me it's going to be in that top corner. And then you want to make sure you graph that hole. So the hole is at 6 and 7/12. So I'd go to where it's 6 and 7/12. You plot that 0, or the hole, sorry, and make sure it's a hole. Like, make sure it's visible. On your test, it has to be visible. For the second one, questions on that one? Okay. For the second one, you're going to factor the numerator, x plus 8 and x plus 1. The denominator doesn't factor. The domain comes from x plus 4, not equal to 0, so x can't equal -4. And the domain goes -infinity to -4, and -4 to positive infinity. Then there's no hole, because nothing cancels, so your vertical asymptote, you can just switch the sign. You'd get x equals -4. This time, the horizontal asymptote doesn't exist because the numerator's exponent is 1 more. So we divide to get slant because it's 1 more. I used synthetic. I wrote out my coefficients. -4 goes on the outside. Bring down the 1. Multiply, put in the next column. Ignore the remainder. And my slant is y equals x plus 5. So then I plot my vertical. The 0 comes from your numerator. There are 2 of them. It's -8 and -1. And then I plotted and the y-intercept. Plug in the zeros and you get +8 over +4, which is 2. And then you're going to plot your vertical asymptote at -4. And then you have to graph your slant asymptote. Your slant asymptote has a b that is 5. And a slope that's 1. So I went up 1 and over 1, drew my slant asymptote. And then the zeros were at -1 and -8, which is on either side. So that told me that those curves are going through there. I added the y-intercept, and then I connected the curves. For your test, which is Tuesday, you have to expect to either have a vertical and horizontal, vertical and slant, vertical and horizontal with a hole, vertical and slant with a hole. Like, there could be any of those combinations. You've got to make sure you know how to go through those steps. There are 2 big graphing questions, and they're going to be worth a big chunk of points because there's so many parts to it. So don't let this hurt you.